Welcome to my new video about heap priority queues. Before we dive in, let's take a quick look at what will be covered in this video. We'll start by defining the priority queues and how they differ from regular queues. Then we'll explore heaps, the data structure we'll use to implement our priority queue. We'll talk through the essential heap operations, insertion and deletion. We also see how heaps can be represented efficiently using arrays, discuss their time complexity, and finally look at some real-world applications. So let's get started. You are probably familiar with regular queues, where items are processed in an order they arrive first in, first out. But what if some items more important than others? That's where priority queues come in. A priority queue is a special type of queue where each element has an associated priority. Instead of processing items in order they arrive, we process them based on their priority. The highest priority item goes first. Now, how do we efficiently implement a priority queue? One common and effective way is using a heap. A heap is a special type of binary tree. First, it's a complete binary tree, meaning all levels are filled except possibly the last, which is filled from the left to the right. Second, it follows the heap property. In min heap, each node's value is less than or equal to the value of its children. In a max heap, it's the opposite, each node's value is greater than or equal to its children. We'll focus in min heaps for the example, but the concepts apply to max heaps as well. Let's see how to insert an element into a min heap. We first add the new element to the bottom of the tree. This might violate the heap priority, so we then bubble up or heapify up the element. We compare it with its parent. If it's similar, we swap them. We continue this process until the heap priority is restored. This ensures the smallest element is always at the root. Now, how do we remove the highest priority element, which is the min heap, is the minimum element at the root? We replace the root with the last elements in the heap. Then we bubble down or heapify down this new root. We compare it with its children. If it's larger than the child, we swap it with a smaller child. We continue this until the heap property is restored. Heaps can be efficiently represented using arrays. The root is at index 0. For any node at index I, its left child at index 2i plus 1, and its right child is at index 2i plus 2. Its parent is at index I minus 1 divided by 2. In this array representation makes heap operations very fast. Priority queues have many real-world applications. They are used to scheduling algorithms, Dijkstra's shortest path algorithm, and Huffman coding for data compression, and many more. Anywhere you need to process these items based on their importance. Priority queues are valuable too. So, to recap, priority queues allows us to process items based on the priority. Heaps are an efficient way to implement priority queues, providing logarithmic time complexity for insertions and deletions. They are a fundamental data structure with wide-ranging applications. Thanks for watching. Don't forget to like and subscribe. See you on the next video. Happy coding.